Once again, we're back from break as promised. Anyway, we were talking about complementary metal oxide semiconductors, or CMOS, and CMOS takes the advantage of combined NFET and PFET properties. As you're well aware, has low power dissipation, at least that's theoretically, and that power dissipation would only happen during switching. Realistically, there's lots of power dissipation due to leakage current, junction gates, etc., and it becomes a significant problem. CMOS, without doubt, is the workhorse of almost all integrated circuit microelectronics. This I took from David Harris. It's basically some physical limits, which we were talking about. Will Moore's law ever run out of steam? Well, you certainly can't build a transistor smaller than an atom, so eventually it must. Many reasons have been predicted for ending the scaling, and some of these have to do with the dynamic power, so that's the switching power, subthreshold leakage, so devices that are leaking or tunneling, electrons or charge that's tunneling through barriers, creating leakage, short channel effects where it's hard to tell the difference between a device that's on or off, fabrication costs, $5 to $6 billion per facility, and one of the reasons there's so few of them around. A lot of companies used to do in-house fabrication, but not so much anymore. Electromigration type faults, where basically the current going through a conductor will in effect create an open circuit. And back in, I guess, 97, interconnect delay was predicted to stop the technology node at 250 nanometers. Sort of in the words of Mark Twain, rumors of CMOS demise has been greatly exaggerated. Moving from the basic transistors, we're going to go to the inverter, and in particular the CMOS inverter. It's the most fundamental digital component. It's implemented with a PFET and an NFET that are connected in series, and it has some really nice desirable characteristics. There's a schematic of it, but it has an input-output isolation. As you can see, these are gates, so no current flows from input to output, and the output is derived from the power rail, so it's either pulled to ground or pulled up to VDD. The inverter building blocks in operation, either the NFET is on or the PFET is on while the other is off. So the output, as I said before, is pulled high to VDD through the PFET, or, and that's an exclusive or, pull low to VSS or ground through the NFET. In either case, no current is flowing from VDD to VSS except during switching. So that's when you're changing the input from a 1 to a 0 or 0 to a 1. And as a consequence, no quiescent power dissipation. That's not really the case, but certainly it's an approximation when you're first learning how to understand how these devices operate and how power is dissipated. One of the main reasons CMOS is or was very good for low power applications because of this lack of quiescent power dissipation. And there are a number of circuit system techniques that have been developed to reduce power. And some of these, for example, might be sleep transistors or power gating. Here's an example of a device. There's a circuit down here which is basically put to sleep under the control of this transistor. So this line here becomes a virtual VDD, and this is a low leakage device. So when it's off, very little charge is leaking from VDD to ground through this structure. If we wanted to look at the AND switching function, basically the construction of AND could be accomplished with either two NMOS or two PMOS, and it's basically a connection of a point A and point B established if both transistors are closed. So in the case of an NFET, you'd have two devices in series, both inputs would be 1 or on. PFET, both inputs would be 0. This is a simplistic view, but not how an AND gate is fabricated at all. An AND gate, if you required one, is more likely to be a NAND gate followed by an inverter. So it may say, well, it takes a little more effort, it's a large number of transistors, but it gives fully restored logic and a full voltage swing. So the output is derived from the power rails if it's implemented in that fashion. So this is your familiar AND function, two transistors or switches in series, in the case of the NFET or the PFET. You may ask yourself what the OR function would be. Well, you can probably imagine if the AND is two transistors or switches in series, the OR would be two transistors or switches in parallel. So here's our basic NAND gate, and as you can see here, I put the N in red there, and this logic block down here is basically the AND. So that is that AND function, two transistors in series, and they're N-type transistors. So this is some switching function, and for example here it's AND. Up here is the complement of that switching function that's implemented in the pull-up section. So you could basically build any gate you like, call it an any gate if you like, and whatever the switching logic is down here, put an n in front of it, and that's the gate. So complement it up here. So 2 transistors in series here, 2 transistors in parallel here. So whatever logic function you want, implement the complement in the pull down section. A and B is implemented as not AB in pull down, not AB is implemented AB in the pull down section. So there's a couple of examples of some functions that you may want to implement. The NAND gate itself, the output of the gate is fully restored, just like the inverter. It's either pulled to 1 or 0, and there's no voltage degradation. The pull down section is called the dual of the pull up section. So the pull down section has 2 N-type transistors in series. The pull-up section has 2 P-type transistors in parallel. A little bit further discussion on that. There's many beneficial characteristics of a CMOS transistor circuit, but there are some problems as well. Some of these have to do with charge sharing, and some have to do with the body effect. And we'll pay a little bit more attention to that a little later when we get into some of the device characteristics. There are, however, sophisticated fabrication and design techniques developed to deal with these types of problems. So they are problems, but they're not our problems. So here's the NAND gate once again. The pull down section, NFETs, or NMOS devices, 2 transistors in series. The pull up section, PFETs and PMOS devices. So that's a little bit more terminology for the pull up and pull down sections of a typical gate. And don't ever put the NMOS device in the pull up section. The reason for that, it's not good for passing a logic 1, where it's very good for passing a logic 0. Just a little bit of FPGA circuits. These are typically lookup based. They're typically based on you can think of them as a small ROM or a RAM. And in effect, every gate looks like every other gate with just the contents of the lookup table changed, basically reflecting the truth table for that gate. And we'll spend a little bit more time on that later. For now, we'll take another little break and be back later.